The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today this is a final lecture and I'm going to talk to you about the future. And if I can figure out how to get the slides going. Okay, predicting future is not a simple thing, and especially this day and age where things are appearing on internet. So this is getting recorded and in the internet, and I'm going to make few comments that in 5 years down the line I'm not going to regret. So we will see. So what I'll try to do is try to have a little bit of a systematic process through that. Because I know you guys are great hackers, you guys actually program, given any problem you can solve it. But as researchers, what's hard and what's very difficult is to figure out what's the problem to solve. Because as Roderick pointed out, when we started on RAW in about 97, there was a raging debate what to build. And there's a group of people who says we can build bigger and bigger superscalers. In fact, there was this article, there was a very seminal proceedings that came out that basically asked many people to contribute, saying what do they think will a billion transistor processor will look like. And about 2/3 of them say like, okay, we are going to have this gigantic fabulous superscaler. And about 3 out of I think about 10, I think about 3 groups said that okay, it will be more like tiled architecture. There's a Stanford people and us are the main people who advocated that. So even that short time ago, 10 years ago, it was not sure what's going to happen. And so we took a stance and spent 10 years working on that. And we were lucky more than anything else that I think we had a little bit better insight hopefully, but also mostly it's a large dose of luck we get here. So part of that is how do you go about doing this. So future is a combination of evolution and revolutions. Evolutions is somewhat easy to predict. Basically what you can look at is you can look at the trends going on and you can extrapolate that trends and you can say okay, if this trend continue what will happen, if this trend continue what will happen. This is very interesting in computer science because one thing I do in 6.189 is look at the rate of evolution that happens in computer science and trying to predict it with things like the rate of fuel economy in cars and stuff like that, and you get these ridiculous numbers. So even if it is evolution, in computer science it's very close to a revolution because every 18 months things double. That's almost unheard of. There are a lot of areas every 18 months you get like 1% improvement and people are very happy. So this is doubling. So we have that. The other part is revolutions. It's some completely new technology or solution just come about and completely change the world, change how things happen. These are a lot harder to predict, but still it's critically important because some of these things can have huge impact. And so we will more focus on evolution, and if we have time at the end, we can see whether we have some interesting revolutionary ideas. But paradigm shifts offer in both. You don't have to wait for a revolution to have something different. Because when things like 2x improvement type thing that happens actually brings paradigm shifts in a very regular basis. So it's not 1% we are getting huge evolution changes, and that can keep changing things. So what I'm going to talk to you about a little bit of trends. I think some of it is repetitive. I mean, I spent some time in the first lecture talking about these trends, and then we'll look at 2 different parts. One is architecture side, what can happen next, and languages, compilers and tools side. And we will spend a little bit time on revolution and just see whether we have good brainstorming. And then I have this little bit of a kind of my view of what people should be doing and very broad level, and I'll finish off with that. So look at trends. I think there are a lot of interesting trends that we can look at. Moore's law, which is a very trusted trend that keep going on for a very long time. Power consumption, wire delay, hardware complexity, parallelizing compilers, program design methodology. So you have all these trends you have to look at. So I had this kind of pictorial graph on the right which shows what happened at every generation. Assume the x-axis is a generation. You concentrate concentrate on the hardest problem. What's the most taxing thing? And what happens is, as you go, at this time, something like this might be the taxing, and that generation, that's where all the design is going on. But then some slowly growing things start catching up, and then after some time, that becomes the most important thing in the design. So it's kind of paradigm shift, because you move into that, focus on that, that becomes important thing. And then some fast moving things start catching up and accelerate, and that becomes a most taxing thing. And then this thing again in a different curve start catching up again. So what happens is you have this cyclic phenomenon too, but and also you have discrete things. So you might get into a kind of revolutionary thing and really bring something down. So for example, we went from very power hungry bipolar devices to CMOS, and suddenly everything shifted down a lot, and then we are back again, we are those power hungry days again, and so that was kind of a revolutionary change and get evolution. So if you want to do work on something, it's not fun working on something that's very important, hot today. The people who are making the biggest breakthroughs on the things that are hot today started 10 years ago. Okay, so you figure out that this is the most important technology today, I'm going to start working on doing my PhD. By the time you are done, it would be passé, most of these kind of cyclic things. So the key thing is, what would going to be hot in 10 years? Okay, that's a hard problem. And so this is the kind of thing you can look at these trends and say, look, these are the kind of trends. This can give you some idea where what might be interesting in there. So are you going to become a low power person? So for example, 6-7 years ago, people who started low power, they made a lot of seminal contributions. People now still can contribute, but they got people who got in early had an easier time, and they will have a lot more impact than people who got in late. And so we look at some of these trends in there and see what we can come up with that. The first trend, this is a very trusty trend so far, is Moore's law. Okay. And basically most of our basis for things happening is probably Moore's law. I mean, basically says you get twice the number of transistors every 18 months, and then that we have had that trend for a very long time. So what's the impact of one trend? So nobody cares about transistors. You can't use transistors, it's in some kind of a closed, you don't even know how many transistors in the processor. What matters is what it can deliver. So performance is what's delivering. So what people have realized is if you are in the superscalar world, this is being flattening out recently. So if you look at it, this is kind of getting flat, and that was a big problem. So that's kind of the reason for crossover for superscalars, I mean multicore. So we are trying to basically get back into again a higher growth curve in here. And then another trend is power. So power had been going in the wrong direction, and also power density has been going in the wrong direction, and this cannot keep growing more than this, and people have problems in that. Something that's really revealing is what's per spec performance. So that means how much power you are consuming to do something. And what you see is we are just starting to waste. We are in a very, I mean, in these days we use very little power to get work done, and now what superscalars did was do more and more wasteful things. And this is what I think led to a big reason for going into multicores, because realize, okay, look, we keep wasting, and now the power consumption of computers are non-trivial. If you talk to Google, I mean, their power cost, power budgets is non-trivial, and we can't just keep wasting that resource. You can keep wasting things when it is not that important, smaller factor, but power becomes a big factor. So how do you get out of this wasteful mode? And I think that a lot of people are looking at that. If you talk to people 5 years ago, people said, this is free. Transistors are free. You can just keep doing things. You just keep them available. Just it's Moore's law makes it free. But what people realizing is while transistors are free, switching them is not free. And switching them requires power. So power becomes an important issue. The other point I point out is this wire delay. As we keep switching them faster and faster, the world looks smaller and smaller and smaller. You can't make global decisions. Okay, and what the implication of that? And we are facing that. I think it's going to get a little bit worse. One saving grace for that is people realize they can't keep scaling the clock speeds that much. So this was this chart I think I did a few years ago. Still the SIA roadmap, that's where the silicon people think where the silicon is going. thought they can get to 10 gigs and 15 gigs and stuff like that. And now they are saying, darn, because of all these power requirements and stuff like that, they might not be able to switch that fast. So there are changes to roadmap because of that. Another interesting thing is, okay, question.
Is that sort of the RC line type wire delay as opposed to? So is that's not speed of light delay? That's including the scaling of the wires themselves.
This is mainly speed of light delay. This is mainly speed of light delay. Because what you do is you just look at clock speed. I haven't done too much of dielectric and stuff like that in here. That's the thing. I mean, you can get closer to speed of light, but right now we are only about few. I mean, we are not even, I think, a factor of. I think we are, I don't know, 80-90% of speed of light. So best case, I think we can get 10% better or whatever. So it doesn't give you that much of room to move. And this is a continuous thing because microprocessors are going much faster than DRAM, and this is having a problem. And this, there are people says there might be revolutionary things happening here, things like volatile, non-volatile RAM might come and kind of take over this area. But what happening today is DRAM now looks a lot more like what a disk looked like 10 years ago. In many ways. So we had to kind of treat a DRAM like a disk. That's kind of really weird way of looking at the world. So here's where I look at compilers and parallelizing. There's no nice number here. So in somewhere around 1970s, people did things like vectorization technique. Question?
Question about the last slide. So when people do this sort of plot versus performance, it's not exactly performance that or throughput that matters relative to DRAM. It's the computation latency, that is the, how fast from when I know I want something from memory to when I really, really need it that matters.
I mean,
is this going to change? Is this possibly going to change as we move to a wider architecture with more parallelism, in the sense that it will no longer be, the latency gap won't be increasing anymore, and we'll start to hear more about bandwidth?
I don't know, because the thing is bandwidth also power. I mean, these are a lot of interesting arguments. This is what you don't know, because the thing is what superscalar people did was we will reduce the problem with latency by predicting and doing extra work. We will try as much as possible to predict what you need and do things in advance. And what happens is as you keep predicting more and more, you actually doing your accuracy of predictions go low. But you keep still increasing the, I mean, anyway, more data, you at least get a small percentage increase in useful data and reduce your effective latency. But accuracy start getting low and it start becoming not useful. So bandwidth probably has the same impact too. So unless you're using the entire thing, you're bringing a huge amount of things, predicting that you might use it. So if the prediction is wrong, it's a lot of wasteful work. And the key thing is, can you pay by power? So I think latency, at some point, if you can't really predict, it becomes hard, unless you have very regular patterns and stuff that the predictions work in there. So if you look at what happened in compile and programming technology, so in around 70s, you get vectorization technology, did well. And then somewhere around 80s, we did things like compiler for instruction level parallelism. That did really well, that got a lot of parallelism in there, very low level parallelism in there. And somewhere in 90s, we did automatic parallelization compilers for Fortran. I think that was almost the highlight of that. Because that year, what happened was we figured out how to take a program written in Fortran and actually do pretty well automatically extract parallelism. Then things were kind of downhill from there. But people said, yeah, Fortran is interesting, but we don't program in Fortran anymore. We are going to program in things like C, C++. That did two things. First of all, one is a language problem, which is C, C++ was unfortunately not a type-safe language. It was not developed to write scientific application, more like operating system hacking that require looking at the entire address space and stuff like that. That really hindered the compilers. Second, programmers start falling in love with complex data structures. Okay, the world is not fixed size arrays anymore. They want to malloc things, have different structures, trees, whatever. These things are much harder to analyze. So suddenly, even though you can deal with nice arrays and loops, people are doing with recursions and these very complex structures, and suddenly the amount of things you can go went out pretty drastically. and you're kind of back to a pretty bad state. And then we are slowly recovering a little bit because things like Java and C# gave a type safe language, became a little bit more analyzable. So I think the automatically what you can do kind of improves. And the hope here is a demand driven by multicores. We'll, instead of, there's no supply technology, but there'll be demand saying, okay, look, you need to do something. And hopefully there'll be interesting things that come about because of the demand. So this is kind of my prediction where things happen, where what happened till now and what's going to happen next. So of course multicores are here, there's no question about that. But I don't think programmers were ready for that. I mean, we have established right now very nice solid boundary between hardware and software, nice abstraction layer. Let's say most programs don't have to worry about hardware. Programmers didn't have any knowledge about the process. In fact, we were moving in that direction. Java said we don't even have to know about the class of the program. We are running this thing in a nice high-level bytecode, write once, run everywhere. Okay, that's a very nice abstraction in there. And for most times, Moore's law actually gave you enough performance that was good enough. We can deal with that. And the nice artifact of that is programmers were oblivious to what happened process. A program written in 1970 still works, still will run 10 times faster. That is really great. If you look at Windows Office, that probably they really took advantage of this. Probably still have code written in 70, but in 80s and stuff. There's still code in there. Every year when they turn, they have this completely new program. Only probably 10% of new code is there. But that's not true for a cell phone. Every time they say I have a new cell phone, most of the time it's actually rewritten completely. So that's why in industry like that, it's very hard to evolve in there because you are just churning too much. And in software, we got really enamored by this ability to reuse stuff, ability to have this nice abstraction in there. And the problem is it provided a lot of freedom for programmers. So they push on complexity. But the trouble is your question about these large companies want complex things. The way people get their competitive advantage is pushing the complexity. So what they did was instead of pushing the complexity of processor, they pushed the complexity of software features and stuff like that. So we are still at the brink of complexity. But now we are adding some another complexity that's very hard to deal with. So okay, so this is the kind of where things came about, how things move. So where can we go? So I want to talk about two different parts, the architecture and languages and compiler. Most of the things I talk about, there's no solution. This is what I think that will happen or should happen. I think that can hopefully will inspire people to go do that. And hopefully I don't have to eat what I say in 10 years. So one thing now about opportunities of multicores is you don't have to contend with uniprocessors. Most of the time this was a big pain when you're doing researching here. So everybody say, yeah, that is very nice, but I just wait 2 years and this will happen for me automatically. Why do I have to worry about your complex whatever you are suggesting in there? And the other thing is, good old days, the people who really wanted performance were these really performance weenies. So in fact, you probably got a good talk from a performance weenie last time who was complicit with abstraction is the evil of all things, and we want just performance at all costs. There are people like that. And for them, producing anything was not easy because they say, I don't want tools. They just suck my performance out. And it was very hard to help them because they don't want help. But right now what's happening is this is getting everybody's problem. So I think that will lead people to wanted things to take advantage of parallelism. Other thing is the problem has changed because people work for 20 years or whatever, no, I guess 40 years on this parallel problem, but that's for multiprocessors. So how does this problem has changed? What's the impact from going a multiprocessor, which is multiple chips sitting on a board or some kind of interconnect thing, to a multiple cores on the same die? Okay, I think there are some very substantial changes that happen that can have a big impact. So let's look at two of them, which is communication bandwidth and communication latency. I think this is where you can have almost revolutionary kind of things happening. So if you look at communication bandwidth, the best you could get if you put two chips on any kind of a board is about 32 gigabits per second. Okay, because you had to go through pins, and pins had a lot of issues in there. But today, if you try to put two different cores next to each other in the same die, the bisection bandwidth is huge. It's 4 orders of magnitude huge than what you can get. That's a huge change. Even for in a Moore's law kind of 2x improvement, this is 4 orders of magnitude difference you can do. So why is that? Because what changes number of wires in a die? Because if you think about it, von Neumann type of architectures is just built to basically deal with this reduction of communication bandwidth. The close things, registers communicates the most, the local memory next, and then remote memory, and then if you had to go remote memory to the next guy, network, these things basically reduce the amount of things you can do. That was really true, because if you have if you inside a chip, you can do a lot more. Minute you go to the board, you can do less. Minute you go to multiple boxes, less, stuff like that. So that is the way the processors were designed. And also the clocks. Within a processor, you can do much faster. In order to go pins not that fast. People are trying to change that, but still there's an issue. And multiplexing, because pins were inherently limited. If you have 1,000 pins, that's a big processor basically in there. And within a die, 1,000 wires is basically nothing. So we have a 4 orders of magnitude improvement in here, and that's amazing. Then it can have a huge impact in here. So you can do massive data exchanges. So one big issue right now in parallelism is the minute you parallelize something, you might slow down, because the thing is you might not get data locality, because that pipe basically get too clogged up because you're trying to take too much data in there. So if you put wrong things, you are going to get clogged by the communication pattern. But this thing says I might not have to deal with that. For example, I don't know why you won't do that, but if you want to move your entire cache from one core to another, you can probably do it in few clock cycles. There's that enough bandwidth. I don't know why you want to do that, because that's probably not memory efficient, power efficient. But you can do it. We have wires. So the key thing is, how can you take advantage of these wires, and how can you make it in a way that you can really reduce the difficulty in programming? Because right now, as you figure out, parallel programming is hard. Okay, if you make a wrong decision, you have to pay a huge price in there. How can you make that in a way that you can make few wrong decisions and get away with it by taking advantage of that? I think there are a big opportunity in here. Another opportunity is latency. This is not as big as bandwidth, because latency has the inherent basically speed of light issue. But again, what happens is now lengths of wires are a lot shorter, and no multiplexing, so you can get a direct wire from there, and on chip can be much closer. And there are other interesting things you can also think about it. Right now, why is register to register communication just very fast? Okay, in a processor, if you send something one register and use it another, it is almost instantaneous, but much faster. Of course, wires delay is close, well, not that, it's very close. Also, there are a lot of other things we do. We move register to register before we even commit the data. So in a normal pipeline machine, you have very long pipeline. The data is externally visible at the end of the pipeline, but I can speculatively send to the next guy and say, you start working on it. If you're wrong, I will yank it out from and say, and then you have to give a speculative part in it. But right now, if you actually go across processors, we can't do speculative. You have to wait till the thing got committed to memory, and then other guys start using it. That's even long than wire delay, because that's like 10-15 cycles I have to wait. Why can't I send something speculative to my neighbor? I have enough bandwidth to deal with it. If I do something wrong, can I speculate across multiple cores, so I can get my data much faster. It's not, then it's probably I'll save probably order of magnitude beyond wire delay, because I have no pipeline stages wait until the commit happens very long later. So things like that can I do in modern process, because now I am putting these darn things next to each other. What can I do with that? And you can do ultra fast synchronization, real time in there. Can I do things lot fine grained across and take advantage of that? So the way to look at that is a traditional microprocessor basically had this structure, basically cache memory and processor cache memory, and this is there because to deal with small amount of wires, power and stuff like that. Today what we have done is basically kind of taken this structure and kind of put it in the same die. Okay, we haven't thought beyond that. Okay, and we get a few orders, a few probably few factors better, because now I don't have to go through the pin, because now I can have instead of we'll say 128 pins, I can have a 512 going or 1024 going in there. But still, I have 4 orders of magnitude freedom in here. I am not using any of those. So one thing Roh tried to do, it have a much more tightly coupled, lot more communication in going on there. So a lot of people say today, the biggest problem in multicores is the network, because now how do I build a scalable network? My feeling is that's balloon. Network is not an issue. In fact, in Roh, a lot of our experiments say we could never saturate a very well done network. Because the network, I have so many pins, I can keep adding bandwidth like crazy. The problem is the way people design a processor core today is to minimize communication going out of it. Have a very thin memory bus going in and out of it. That memory bus can never saturate any kind of network you can build on a microprocessor within the die. It works. It matches well if you have to go through the pins, because it probably matches that. But within the die, you have so much more bandwidth. So I think something interesting would be kind of fundamental redesign of what the microprocessor looks like, the core looks like. It's not taking a Pentium and kind of plopping it once or plopping it 4 times. A Pentium is not. Any kind of a nice processor had evolved over the years to basically deal with this very thin memory bandwidth. Okay? And suddenly you got 4 orders magnitude of that, and that problem goes away. And we are still saying, okay, yeah, I have this entire thing in there, but I only want 4 wires out of you, or 1024 wires, when you can give me 100 million wires to me. That is the question. So I think there will be some interesting things. I think people can make a big impact trying to figure out how to take advantage of that. And by doing that, really reduce the burden for the programmer. Because right now we say, okay, look, I am not taking advantage of that, but I am passing on that back to the programmers. They have to deal with all that small interconnectivity. And then we can say, oh, we can't use that because programming is hard. So how can I reduce the programmer burden? By taking advantage of that. I think this is a very interesting way to go look at this problem. So if you are doing any architecture kind of research or interested in there, here's an open problem. I have this huge bandwidth out there, and I have evolved something that is completely, in a way, dealing with very limited amount of bandwidth, because that's what they lived for this long. And the minute you open it up, how can I deal with that? I don't think we have a model. And I think there's a lot of interesting work can come out there. Okay, let's switch to language compilers and tools. So the way you look at that is, what's the last big thing that happened in languages in there? I think one that happens is object-oriented revolution. The interesting thing about object-oriented revolution is it didn't happen in a vacuum. It happened because a lot of interesting research in academia and outside went into it. People didn't come up and say, objects are a great thing, I'm writing Java. There were hundreds of languages that developed and explore these concepts. And the interesting thing about programming is a lot of things that looks very neat and interesting when you look at it first time. Minute you start using it in a million-line program that has to evolve over 10 years, you realize that's a pretty bad concept. Can you anybody think about a concept that looks very interesting at the beginning but actually very hard to deal with?
I just named my last girlfriend.
Well, okay, I haven't heard about that analogy before, but hey, what else? So for
Exceptions.
Exceptions, yeah, I think exceptions people still haven't figured out. I think one thing people have made assumption, things like multiple inheritance. When multiple inheritance first happened, they say, wow, this is the best thing after sliced bread, because the thing object-oriented programming does is it forces this one hierarchy. And the world is objects, but there's no one hierarchy in the world. World has this multiple interconnections in there, and so people say, look, this is great. This basically now you get objects, and you can get a lot of different relationships. But after people try to deal with multiple inheritance, you realize this is a pain. It's very hard to understand it, very hard to write a compiler. There's so many ambiguities around it, and then at some point you just say this is too much. And that's why you went to, like, Java went kind of multiple inheritance light by having, you can inherit multiple interfaces. But but here's a concept that looks very nice, but you had to work. It took 5-10 years to realize that it actually is not usable. So if you look at object-oriented languages, there had been many languages. So this is interesting thing, because in parallel community, we haven't had this kind of explosion out there. Another interesting thing about languages is language has lot of relationship and evolving. So if you look at from Fortran that started, you can't see the Fortran, so this is Fortran in here. To figure out what's happening today, you can kind of trace over the years how new languages academically and industry came about, got influence from others, and at the end up with things like right now at the end of the graphs there's something you can never read it, but the key thing is there's all these influences going across in there, and cross fertilization. And at the end, you end up with something Tickle TK, Python, I can't even read it carefully, Java, C#, PHP, and stuff like that. So there are a lot of different languages trying to get influence in there. So the key thing is you need to feed this beast if you want to have a lot of evolutionary or even revolutionary changes. And the languages has to. What that means is. People say, yeah, we have Java, C, and C++, C#. We are happy with languages. No, I think the future to deal with that, you need to have kind of revolution in there. So if you look at something like C++, there will almost every language start with Fortran, so because that's in there, and then there have been a lot of different influences that happen through that. And I'm going to just go over that, like for example Java, this is acknowledge that a lot of these different languages influence that ideas in there. So why do you need new languages in there? I think we have paradigm shift in architecture. Because sequential to multicore will require a new way of thinking, and we kind of need a new common machine language for these kind of machines. And there are new application domains, because like for example streaming is becoming very interesting. Scripting. People are using things like Python and Perl and stuff like that in a much regular basis to do much bigger things. And okay, so those are kind of cobbled together languages, but can you do better in those kind of things? Real time, things like cell phones and stuff become more important. How do we deal with those issues? And also new hardware features. So right now languages are almost tied. Good languages are tied very well with the von Neumann hardware features in there. So things like when you can, for example, when I tell you that you have all these wires available, if you figure out some new way of taking advantage of those wires, that hardware feature, what's the software that can really utilize that? So you can just build a hardware feature, it's not sufficient, you have to have a software to deal with that too. So what's the coupling there? I think there will be a lot of things that has to be that nice interconnection there. And I think there are new people who want it, mobile devices, average programmer. If you look at parallelizing compilers, so parallelization before was always geared toward this high performance weenies who just wanted to get their global simulation going as fast as possible, who has a multi-million-dollar supercomputer waiting in there. It's very different having things like average programmers who wanted this. So how do you cater to them? They are very different in there. And the key thing is how can we achieve parallelism without burdening the programmers? Because we basically in this class we really burdened you guys, and then you realize how hard it is and how much more complexity it adds on top of the algorithm just to get it working parallel. So how do you kind of reduce some of the burden? Perhaps not completely eliminate, but really reduce that burden. I'm going to skip some of this. I will make it available on the slide because I want to have some time discussion. So in Stream we talked about it. We try to do some of that. Try to come up with a programming model where it will give you some additional benefits to program. At the same time, we can actually get multi-core performance. And of course, we saw that in the compiler we can actually get good performance in there. So one thing that I did long time ago is this Swift parallelizing compiler. What we did is we can automatically parallelize Fortran programs all the way in. This kind of almost worked in 90s. We in fact at some point the spec benchmarks were the way to basically measure how good your world is, and every company had 20 engineers trying to get 5% out of spec, and at the time where spec performance was about 200, while I was a graduate student, we did this compiler that we could get spec benchmark at performance at 800 by just parallelizing. And in fact, we made this T-shirt that said spec rate and the number. That's all the T-shirt said. And in fact, I was working in a few places, including the grocery store at Palo Alto, and people stopped me and said, "How did you do that?" And it's only on this kind of weenie things. And then I had like, in this grocery store, I had like half an hour conversation with the engineer's son of how do you get, because he was like, "Oh God, I mean, the only thing spec 823. That's the only two things that the T-shirt said. People knew what it is." But there's problems. The compiler was not robust. The compiler can be used by the people who wrote the compiler, because we knew all the things in there. The thing about that is it worked in a way that if the program worked, you get 8x improvement. You change one line of a code somewhere, you went from 8x to 1x. Okay, because that entire thing stopped parallelizing, and Amdahl's law kick in, and so now normal programmer can never understand what happens. So we go analyze it, and after time say, aha, this is how to change the program, or this is how to change the compiler. So it was kind of developing program and the compiler at the same time, and we could use this thing. And so you cannot ignore the fact that this is happening, because there's so much of a difference in performance. That makes it even a curse. I mean, if you only get 4x improvement, probably things would have been better. We should have probably capped the performance or something. And clients, those days were impossible to work with. You saw a very good example in last lectures. Okay, performance at any cost. I don't want any of these tools if it slows down at any time. So how do you deal with those kind of people? It's hard. And in multiprocessor, communication was expensive. So if you make a wrong decision, you pay a huge price. Basically slow the program down. So you go from, instead of 1x, you actually go from 0.5x, and that's worse. And you had to always deal with Moore's law. You say, okay, why do I need this complicated compiler? Just wait 6 months and won't I get it? And they're probably right at that time. And there's another problem, what we call the dog fooding problem. The reason that object-oriented languages were very successful is everybody who did an object-oriented language, and you want to get accepted as a reasonable language, had to write their own compiler in that language. And a compile is a very good way of really pushing object-oriented concepts. And so almost every object-oriented language wrote their compiler. That's a really big thing you have to write. And by the time you write the compiler, you realize all the problems with the language, your language got really improved, because you have to write a few 100,000 line program in your language. Except all the people who were doing high performance, we were catering for somebody else. What that means is we can deal with this weirdness and say, it's no problem, nobody, I don't. But those are the things that really kill the users in there. We didn't have the user's perspective. But another thing that today is things are very different, because we have complex data structures, complex control flow, complex build processes, alias type unsafe languages. So all these cool things we used to do just became 100 times harder because of all those things. People fell in love with data structures, and they say, damn, arrays, they were so nice. We knew exactly the same size thing, it doesn't change, I could analyze it. But malloc data structures is just, and very complex trees and doubly linked lists were just impossible to deal with. So we want to go in the days where everything is a nice simple array. But hey, I guess the task for the compiler became much harder those days. So I think compilers are a critical thing to deal with. I think if you have to improve in multicores, you have to deal with compilers. And the sad thing is, some of those things people are trying to do it today by hand. We could do it in the compilers 15 years ago. We kind of lost that technology, and people are kind of doing this by hand again today, and kind of go back and kind of dust up this technology and bring it back in there. In best case, we might be able to automate everything and say, look, don't worry, right? Do what you are kind of doing today and just keep doing it, and we'll just get multicore performance. I don't think that's going to be that realistic. But in worst case, at least we can help the darn programmers. Tell them what's good, what to do, when they do something wrong. How can you build those kind of things? I think that's very important. I think in tool side, we need tools. I mean, you realize after programming on Cell that it would have been really nice to have few tools. I guess everybody can probably come up with some tool suggestions. And I think tools in this one is pretty ancient. How do you come up with really good tools that the normal programmer can use them, figure out problems, figure out debugging issues and stuff like that, and get through together. So kind of we need something like Eclipse type thing for platform for multicores, where a lot of nice plugins come about that actually help you do that. So another interesting thing, this is about this dog fooding problem. is normally what you come up with is a language compiler tool. You do implementation, you do an evaluation of that, and you kind of cycle through that. And evaluation says, okay, you develop a program, you debug the program for functionality, performance debugging, evaluate, and everything kind of go around that. I mean, there's this process in there, and you run and realize some things are very hard to do, some things are easy, and you need that to basically evolve that. And the problem is, I am contrasting two things. If you look at something like CAD tools were developed by a bunch of guys sitting in places, used by some very different group of people. Because of that, today's CAD tools are horrendous to use. Everybody hates them, because the people who developed CAD tools never thought about the users. They were different, and they just had to get the functionality out, and they were very happy after that. Whereas something like object-oriented languages were a lot more thought about as how the best way to use it, very much of a programmer-centric way. And I think in that end, you develop a system that's a lot easy to use, a lot of people use it, a lot more acceptance in there. The problem with high performance languages is they kind of really sit in the CAD tool layer, because the people who write high performance languages never really use it. The people who write the compilers and languages are not the one who developing the high performance programs. No high performance language ever wrote the compiling that language, because they say, oh, that's a different domain, we don't have to do that. But by doing that, you really never expose the problems in there. And I think the key thing is, how do you go about doing that? This is a hard problem, because how do you get the two different groups together? And perhaps multicores, what it will do is, you probably everybody who write the compiler and tool actually will have to write it in the thing they are developing, because you need the parallelism. At that point, you will realize all the problems with the tools. So I'm going to skip on this side. Another very interesting problem that people don't pay attention is the migration of Dusty Deck. There's millions, if not billions, of lines of code out there written in old style ways. You can't just say, yeah, look, Microsoft, just go rewrite everything new with my sniffy new system. That doesn't work. How do you get these people to kind of migrate out through in there? And that might not mean do it everything automatically, but how can you even help? The people who wrote the code is probably now gone, left the company, probably dead. How do you help somebody move some of these things new? I mean, that is the way to do evolution. You don't have to rewrite everything again from scratch. So what kind of tools that you can use? And in this, these applications are still in use. Sometimes source code is even available, but programmers are gone. But the interesting thing is, some of those things, applications have bugs that had become features. So I'll give you a very good example. In this happened to Microsoft. So at Microsoft, at some point, if you know Word has algorithm that paginates. That means how to lay out the pages and how to break pages and stuff like that. So they had the algorithm in there, and they were switching versions. And they said, look, this algorithm is now too old, been there for 5-6 years. We have to rewrite it. And of course, you can assume what the spec is. There's a nice spec to that, few pages, and they said, okay, go rewrite that. And somebody wrote a very nice pagination algorithm. But the problem is, when they use that algorithm, lot of old documents broke. That means they didn't paginate right. So the old documents, when you open, it looks very different. And they said, darn, what's going on? What they realized, so the old implementations had a lot of bugs, subtle things, where it doesn't really conform to the standard. So it didn't break the word exactly right. Instead of at some point it has to break and space, it probably put it on the next line. Few things that didn't really do that. And what they had to do is they had to spend a lot of time discovering bugs and adding them to the spec. And so they went about, because otherwise all the previous programs doesn't work. Previous files will not look right. And they went through this entire process of trying to discover and trying to figure out what the code did instead of what the text of the spec said, because they were out of sync. And so a lot of times there's that problem. So you assume you have something old and you want to create new. It doesn't mean that you know the functionality. The functionality that was implemented is the spec, not the functionality you wrote about, because that's a little bit subtly different. So how do you go and discover that? I think that's a very interesting and important problem. And I think there are many recent advances, things like creating test cases, extracting invariants, things like failure oblivious computing type. If you had listened to Professor Reinhardt's talks, things like that can help take these all things and migrate. Can you build some tools to do that? I think there are a lot of interesting research in there. Okay, so that's kind of my take on languages and compilers where interesting things can happen. I won't talk about revolution, but I want to skip that first and go into this crossing the abstraction boundaries part, and then come back to revolution. So the way the world works is you have some kind of class of computation you want to do, and you have some atoms that actually you need to run that computation on. That's basically the end to end of any process, okay? And but if I said here's some silicon and here's my algorithm, go do that, no single person can basically bridge that gap. Okay, you can't take silicon and go to semiconductor process, build a process, design, all those things, language, everything doesn't happen. And if someday it probably was possible to have one person know everything, but you can't. So the way we have deal with that is build abstraction boundaries. We have compilers, languages, instruction set, microarchitecture, layout, design rules, process, material science, physics, everything is separated nicely. Every time one gets too complicated, we cannot divide it in half and kind of keep adding and adding, and we have this big stack of things happen. So at the beginning, when you break up, people kind of knew both sides, and they went into one side and kind of broke that up. And then people knew a lot of things. But the next generation comes, they only know that. The guy, someone who's going to be expert in microarchitecture. He only know microarchitecture. He has no idea what the languages are, because that world itself is complicated. So what we have done is a compartmentalized world that was broken up as we went in last 40 years. As things progress, the right thing at that time, they figure out what layers to do. What he had done is created this domain experts. There's one guy who's probably know about two things. He might know a little bit of design rules and probably process a little bit. Another person who know a little bit design rules, layer and microarchitecture. And there's somebody who's doing microarchitecture and ISA. And somebody knows compilers and ISA but had no clue what's happening. So what this has done is kind of we have entrenched in some layering that really made sense whatever 30 years ago. The problem now is this is creating a lot of issues in here. So what you kind of really need is the way to break some of this layering. So how do you do that? So you need people who can cross multiple of these disciplines. So this is a thing for you. I mean, you might think you are architect, but hey, you are in this class, you learn a little bit of programming. Go learn a little bit of physics. What's in there? Just have a little bit broaden in there. Then a lot of people, there are some people who are a lot more in the process side, but know a little bit about microarchitecture and compiler. Somebody in the middle, they are expert in the middle, but they are not just sitting in happily in their own domain. Just try to look at cross-cutting in there, and keep going up in some sense. I kind of put myself in there, saying, okay, I'm in compilers, but I know a little bit of language, and I try to go down and down as much as possible. What you actually need is somebody who knows everything really well. That is hard, but at least somebody who kind of know the top and the bottom to redo the middle. Because my feeling is the way the middle is done is probably now too old. So I don't know whether this is possible. It's not me. But if somebody really understands the top and the bottom, and say, okay, I can probably throw the middle and redo the middle, and I think that might be interesting revolution that might happen. It's hard. There's so much information in there, but some of those information are there. The layers are there. It doesn't make sense today the way things happen. I mean, like for example, a lot of these layers had issues with wire delay, because when wire delay was not an issue, these layers made perfect sense. But as soon as wire delay came about, a lot of changes had to propagate across layers, and it was very hard because people were domain experts. So I think this is where the revolutions will come. Somebody's going to throw the entire middle off and say, look, the way you do compilers, the way you do architecture, the way you do design, everything is wrong. I know the algorithms you want to run. I know what's available in very low level physics. Let me redo that, put them together. A person, a group, whatever, might have a big impact. So with that, I will go to the revolution side. So the way to look at revolution, so what are the far out technologies? And sometimes revolution just come from wishful thinking. You say, I wish we can do this, and if you can push hard, you might be able to get things like that. Anybody wants to? So in this talk, I've talked way too much. How about comments? Where do you think this is going to happen? What do you want to work on? You guys are the ones who have to make this decision, not me. I'm already made a lot of decisions myself 10, 15 years ago, what I'm going to do. You are in the process. You have a lot more choices to make decisions. You haven't narrowed your horizon yet. And so this affects a lot more on you than me at this point. What do you think is going to change the world? what do you want to work on? I mean, you should work on something, I guess, probably you think is going to have huge impact. Have you thought about that? A lot of silence, more than I thought.
Oh, just working on our project, we'd like much faster communication between the SPUs. So you take the communication bus, imagine that they're actually just one processor.
So faster means bandwidth or latency?
Latency.
Okay, latency, yeah. The latency is a hard problem because so there are a lot of people who are trying to do latency hiding techniques.
Yeah.
And then on the revolution side, people like looking at quantum computing and quantum effects, trying to kind of do kind of physical breakthroughs in to deal with latency.
Yeah, just synchronizing the processors is hugely.
Yeah, I think there are a lot of evolutionary things you can do there, especially with taking advantage of the fact that you have a lot of wires in there and stuff. I think people haven't really pursued that yet, and this is where the complexity will come in. Not trying to basically deal with these, taking advantage of these kind of things. I think there are a lot of opportunities in there, and then that's the kind of evolutionary path. And then some people are working revolutionary things like quantum. What else? I expect people to have a lot more interesting insights on this.
One clear trend that I think you mentioned it, but you didn't really like in the trends thing is mobility, right? Moving mainly towards mobile devices.
I think world is almost bifurcating. There's things that you can have a power plug, and there are things that kind of don't have power plug. And I think people who have power plugs still have some power issues, like what Google is finding out. You can't just keep wasting power. But as things start become mobile and things start just going into smaller and smaller devices, their power and the size becomes a much bigger thing than what more you can do. So you don't become a performance fiend. You want some level of performance. You need to get a video, but the minute you get the video, you don't want to have HD video. You just say, okay, just get a video onto my cell phone screen. I'll be happy with that speed. Just do it as low power as possible, as low cost as possible. So I think that's that push in there. So for example, interesting thing, for a long time what has to happen is there's a trickle down economics, things that start happening in the very high end system and kind of trickle down to the low end. But there might be a diversion in here. There might be a different path coming up because that trickle down might be that technology might be fundamentally different. So
I think one thing that's also changing from the software side is this notion of perpetual beta. I've been using it, you just mash up code, you put it up on the web, lots of people use it. So maybe it's pushing for scripting-like languages or whatever else.
So this is an interesting observation I had. So while I was a graduate student, I wrote a lot of code. And they became a professor, and I basically barely had time to write anything large, just a thing. And then a few years ago, I did a startup, and I just had a time to write not large as well as graduates, and some large piece of code. What I realized was what programming had become is the best tool for programming at that time was Google, because I was trying to do a bunch of things with Windows, and everything I want, there was a function, and if I can find that function, my work is factor of 100 smaller. So I spend more time than actually think about algorithms, how the list should be or how my data structure should be, trying to Google it and say, done, I won't do this. Where is that function? Where can I find that function in this entire big library? So what that means is there's kind of this missing layer in there. Because what has happened is the thing is our languages suppose a level of abstraction. And then we have built these libraries with no kind of support at all. I mean, the compilers, languages don't really support the libraries, because it just build out of basic blocks. And the key thing is, can you have better basic blocks? Can you have more nice abstraction? Instead of saying, okay, here's 5,000 libraries with 250,000 different functions that you can use for something. Can you build it in a nicer way?
So what might be interesting then is, you come up with a standard for the interface, your input, your output, and then you publish your code, and then Google indexes for you. And then your program is just a collection of Google searches.
I mean, if you think about if you think about what all the Windows source base is, it's like that. I mean, in the company we were doing, it was doing the security product. There was this group of people who understood every line of code they wrote because they were writing a virtualized virtualization system that runs under Windows. So for them, every line was probably there. The interesting thing is when that group started, that entire piece of code was about 50,000 lines. Now it's about 65,000 lines. But we had about 10 people working on that again and again. That means these things get revised. You don't keep adding. And there's another group of people who's doing user interface and stuff like that. They have alphabet soup of different libraries. They are using Ajax, this, that, and that. I don't even know what they are using this. And the amount of code they write is immense. Amount of things they have to know is immense. Each of them are not that complicated. But to get if you use a bad thing, you have a bad looking interface, clunky, slow, whatever. If you figure out the right 3 function calls, things look much better. That's a very different type of programming in there. So for them, it's a basic knowledge. How much things you know. It's almost like I remember my college days, friends who were doing things like in medical school. So you need to know this entire thing about all the different muscles in the body, and there's this big thing book you just study. It's almost like that. You just take this big Windows manuals that are like few hundred pounds heavy, kind of, and you look at every page and figure out what you know. That's kind of really strange way of coding. But I mean, algorithmically, what they were doing is pretty simple. I don't think they ever designed data structure. Just every data they used came from something, but they had to figure out the right data structure.
This is going in a totally different direction, but in terms of graphics and video games, perhaps getting artists who are aware of both the hardware and the software, and so can design more for the capabilities of the machine and can make more visually appealing.
Yeah, I think that's the area that also has a very different set of communities. I mean, artists are completely like not even trained engineers, and they're sitting in one end, and they have these neat features. They want to look natural or whatever it is. And then there's the programmers and hardware people that who knows what the capabilities. I think that's what we were trying to push in Mike Acton's talk and say, okay, how do you go about it? How do you know that when the new thing comes, what is doable? Like for example, what ATI does is ATI has a group called the research group. What they do is every time a new chip comes, they actually go and figure out all the things you can do with that thing. Okay, how can you do rain in this one? How can you do? So they write a lot of kind of, those are a little bit artistic bent, but very hardcore programmers who kind of figure out what's doable, and they make that available and say, hey, this is what you can do. And I think a lot of people kind of emulate that. They say, wait a minute, how did they do that? Then kind of figure out, okay, now I have this new hardware and I will be able to do something completely new. I think there's a push in there. I mean, I think this is where interesting revolutions come about. I mean, one of my firm beliefs is a lot of good research is not in one area, as I pointed out. It's kind of looking at very two distinct things and kind of bringing them together, bringing knowledge from one to another and mixing them together. I think that can have huge impact-wise. So that's a place that I think can have huge impact. What are the things that will have big visual impact that the next hardware can enable? And you can keep adding more pixels and stuff like that, but it's not the thing. What are the things that can have big impact?
So it's not just gamers, right? It's the same is true for biologists, physicists, chemists, right? End users. So maybe the thing to do is work on language generators, right? An easy way for me as an end user to express the language domain that I want, and give me a way to generate it.
So I mean, there's a lot of things. For example, I was talking to this computational biologist, and what he said was, for computer science, the best thing that happened from biology point of view is Excel only had 32,000 cells. Because the biologists keep using Excel and they said 64,000 cells. And when they ran it, they said, geez, I can't do anything more in that, and now what do I do? And suddenly they had to start looking at programming and stuff like that because they can't have Excel spreadsheet doing that. So I mean, that's a lot of biologists actually had to switch. So I think interesting thing about the computer science is there are a lot of fundamental sciences still, but I think we have grown so and ran so fast developing that. I think what's lagging behind is applications, how to apply that to biology, gaming, stuff like that. And I think there are a lot of interesting things as computer science we can do is to bring that knowledge and kind of in applied community. They will be like really, you can have huge impact and fundamentally change things if you kind of apply that knowledge, both theoretical kind of things we have figured out, as well as using the power if the computers we got in the right way. I think a lot of times people are kind of doing what they used to do 2 times better, 5 times better than kind of seeing fundamental switches. I think this is interesting topic. I think I'm going to stop soon. I think it's interesting, especially for you guys, because you are probably going into area, looking at a field, trying to get expert in something. There's a lot of times you get seduced to become expert in what's hot today. But the interesting thing is, especially if you're doing a PhD or if you do something that takes 4 or 5 years for you to mature in that area, is it going to be the hottest thing in 4 or 5 years? So multicores are hot today. So should I recommend that everybody jump and become expert and try to do a PhD in doing multicores? Probably not. Because 5, 6 years down the line, some of these things might be solved. It better get solved. Otherwise, we are in big trouble. Okay. But the thing is, what's going to be the problem then? I think one thing that's very hard, it's almost art, is to kind of go and pick few of those things and then put 2 energies there. And if you're lucky and if you had done a good job in that prediction, you'll come about, and by the time you get to a point that you become expert in the thing that's most important. It's not an easy thing to do. And a lot of times, nobody can claim that they have technique to do that too. A lot of people who claim are discounting how lucky they were. There's a large amount of luck associated with it. But the key thing is to kind of follow that trend, identify and do that. And that's a technique that I think every one of us, every one of you should develop. Okay. With that, do you have to say something about the?
Yeah. So a couple of things about Final Fight. Anybody here want direct access to the PlayStation 3? I know a couple of groups have been asking. Just 1? 2. Okay. So come by. Actually, if you have time now, we'll talk about that and figure out a way of getting you access to it. The final competition is going to be this Thursday. We got the big auditorium room